Here we're going to talk about the derivative for parametric curves. They're going to follow the same idea that we got from the chapters that covered derivatives for lines, which is that we're going to look at t as it gets very, very small, as the limit of the difference in t, the change in t or delta t, approaches zero. And what we essentially get is the separation of the two curves with respect to t. And so we just take the derivative of each line, y and x, separately and stack them to create what is essentially a slope, because if you recall, derivatives are trying to give us the slope at a specific point. So we're just going to go back to our normal definition of slope, which is what this slide and the write-up in the book are trying to explain, which is essentially we're trying to build up some lines, some secant and tangent lines, to be able to reduce this to a common slope. So the math ends up being very straightforward because all we have to do is take the derivative of the numerator and the denominator. So it's just our typical derivatives. We just have to remember that it's with respect to t. What does get a little bit more challenging is trying to figure out where the dy dx is undefined, because we're going to have to set the numerator and denominator equal to 0 and then double check. And then even when we do that, sometimes we'll miss points altogether. So let's try something with this line up here. We have these two lines, x equals t and y equals 2 root t. And we need to look at their derivatives. So x equals t and y equals 2 root t. If we stack these and take the derivatives, we get, let's see, moving the 1/2 out front would cancel with the 2, so we just get t to the negative 1/2 over 1, which is better known as 1 over root t. So our derivative is 1 over root t. We could write that as dy dx is equal to 1 over root t. Anywhere this guy is 0 is going to give us a hard time, and we can see that as this curve approaches 0, we're going to get a straight up and down line. So as we expected, at 0, we have an undefined slope. And that's really what we're trying to get out of these, is if the numerator is 0 and the denominator is not 0, then we'll end up with a flat line. And if the numerator is not 0, this does not equal 0, and this does equal 0, then what we end up with is a straight up and down line. And that can help us out a lot when we're trying to graph stuff that's not familiar. So if we go back and look at the next slide, that can help us identify all of the flat pieces of this graph and all of the straight up and down pieces of the graph, just by solving for 0 in the numerator and denominator and looking at especially the case of 0 over 0 very carefully. We'll cover this more when we go over how to graph in polar, because this will come in more handy there. For these kind of equations, we would be able to graph these because these are an ellipse and they're given in sort of the normal way that an ellipse would be given. When we hit polar equations and we hit polar graphing, then we'll see that this method of being able to come up with where the lines are straight up and down or horizontal will come in a lot handier.